Okay, so good morning to everyone present here. My name is Shashwata Samanta, and we are going to present my presentation on the topic of computational complex theory. In this session, we will explore the fundamental concepts of time and space complexity in the computer science and theory of computation. Join me in unraveling the mysteries behind the efficiency of an algorithm and limits of computation. The vast landscape of computer science, understanding the efficiency and feasibility of algorithm is a fundamental pursuit. Computational complexity theory deals with the interactivity of the problem solvability and resource requirement and inherits the difficulty of computational tasks. In this presentation, we will embark on a journey to unravel the complexities of computational theory. We will start by explaining the basics of space and time complexity, what they are used for, and then shed the light on the crucial measures of algorithm efficiency. We will then explore the distinct realms of P, NP, and NP complete problems and the implication they hold to solving the computational challenges. But first, let's dive into what's the basic of computational complexity. So computational complexity is study of the resource required to solve computational problems. It focuses on understanding the time and space requirements of an algorithm. By analyzing the efficiency and stability of algorithm, we gain the insights about the particular algorithm and get to know how it is useful for us and what is the disadvantages it holds. Now, before going to this, I just want to put a little bit light on what basically is space and time complexity is. The time complexity of an algorithm measures the number of computational steps required to solve a problem, whereas the space complexity of an algorithm measures the amount of memory space required to solve the problem. These two crucial things help us to determine how efficient an algorithm is and how well an algorithm works in a particular scenario. This helps to understand and study the algorithm more properly and helps us to make it better. Now, as we are on this topic, let's get into the most important part of this presentation, that is complexity classes. Complexity classes are basically of five types: P, NP, ONP, and NP hard. If you can put your focus on your set screens, you can see this basics given of every type of complexity classes is given and this Venn diagram. We'll discuss about all of this in detail in the further slides. So, in this realm of computer complexity theory, computational theory, one of the fundamental concepts is of complexity classes. This classes plays a crucial role in classifying the problem based on their inherent difficulty and resource required to solve. A complexity class is collection or grouping of computational problems that share certain properties typically related to their solvability within a specific resource constraint. This classes helps us to understand the relative difficulty of the problem and provides a framework for analyzing the efficiency of an algorithm. Now, after this, we'll discuss each one of these complexity classes in detail from the next slide. First comes the P, or the polynomial time. Complexity class P comprises problems that can be solved by an algorithm in a polynomial time. In other words, for a problem to belong to P, there exists an algorithm that can solve it efficiently within a running time that grows on faster than a polynomial function of an input size. These problems are considered tracular as they solve can be obtained within a reasonable amount of time. Basically, this is basically a class in which problems lies which are can be solved on a given polynomial structure, like in a given polynomial time. Next that comes in this list is NP. NP or NP non or the non-determinable polynomial time and NP complete problems. The complexity class NP encompasses the problems of which a potentially solved can be verified in polynomial time. While NP stands for non-deterministic polynomial time, it does not necessarily imply that the problem can be solved efficiently. Rather, NP focuses on ability to verify a given solution efficiently. If a potential solution is provided, it can check it polynomial time to determine if it is correct or not. However, finding the solution itself may require many more time. Next is NP complete problems. Represents the most challenging and compressive subset of NP. NP complete problems are considered the hardest to solve the problem. They are characterized by property that any problem in NP can be transformed into them in a polynomial time. In other words, if an efficient algorithm is discovered for an NP complete problem, it will imply that all problems in NP can be solved efficiently. Now, in this topic, one of the most major topic that comes is what is the difference between NP and P. The P versus NP problem stands as one of the most profound and influential unsolved questions in computer science. It addresses the relationship between two complexity classes P and NP. The implications of solving the problem would have far-reaching consequences, impacting various fields within the computer science and beyond. The P versus NP problem can be stated as follows. Is every problem from which a solution can be verified efficiently also solvable effectively? In other words, does P, the class of problems solvable in polynomial time, equals the NP, the class of problems for which solution can be verified in polynomial time? If P equals NP, it will signify the efficiency of algorithm exists for all the problems in NP. This would fundamentally alter the landscape of computation science and have profound impact. Many computationally challenged problems such as optimization, scheduling, cryptography would suddenly become solvable efficiently. Potential breakthrough resulting from a P equals to NP solution could revolutionize the industry, advance scientific research, and transform the way we approach real-world problems. Conversationally, if P does not equals NP, it implies that there is a problem within NP that is inherently difficult to solve effectively. In this case, finding an efficient algorithm for such problems would be highly unlikely. The P is not equals to NP scenario suggests inherent limitations on computation and raises question about the boundaries of algorithmic efficiency. It would confirm the existence of the hard problems, quotations, as we call it, like the difficult ones. It would confirm the existence of the hard problems that cannot be solved easily with optimal solutions with the optimal set of time. The importance of P versus NP problems extend beyond computer science theory. It has practical implications in cryptography, where the security of many cryptographic protocols relies on the assumption that certain problems are computationally hard. If P were equal to NP, it would have significantly coincide into the information security, as it would imply the cryptographic system could be easily broken. Furthermore, P versus NP problem serves as a benchmark for progress in computational complex theory. It represents an intellectual challenge that have captivated researchers for decades, inspiring the developer of the new technology, algorithm, and problem-solving methodology. It has motivated breakthroughs in related areas such as discovery of NP complete problems, which are critical for understanding the complexity landscape. Despite numerous efforts, P versus NP problems remains open and elusive. To date, no conclusive proof has been found to settle the question. Question is whether NP is equals to NP or not. The Clay Mathematical Institute have introduced the P versus NP problem as one of the 7 Millennium Prize problems, offering a $1 million prize for this resolution. In conclusion, the P versus NP problem encapsulates the quest for understanding the fundamental limiting and possibilities of efficient computing. Solving the problem would have profound implications impacting computer science, cryptography, optimization, and beyond. It unresolved status continues to challenge the researchers and inspire advancement in the computational complexity theory. Next comes the applications of this complexity computational theory. Computational complexity theory, with a deep insight into the inherent difficulty of the computational problems, have several practical implications across various domains. Here are some of the practical implications of the computational theories. First is algorithm design and efficiency. Computational complexity theory guides algorithm design by providing a framework for analyzing and improving algorithm efficiency. It helps identifying optimal algorithm for solving problems and enables the development of more efficient and scalable solutions. Second, classification and solvability. Complexity classes such as P, NP, and NP complete helps classifying the problem based on their inherent difficulty and resource requirement. This classification assists in determining which problem can be solved efficiently and which is likely to be computationally hard, allowing researchers to focus on their efforts and research accordingly. Optimization and third is optimization and resource allocation. Computational complexity theory plays a crucial role in optimizing the problem, where we finding the best solution for the large set of possibility essentially. By understanding the complexity of optimization, a researcher can understand how much resource need to be given to that particular problem and how it should be tackled. There are multiple more applications for this, but we will restrict ourselves from this three only. Now, jumping to the conclusion part. So, in conclusion, computational complex theory provides a formal framework for studying the efficiency and limitations of any kind of algorithm. By understanding the time and space complexity, we gain valuable insight in the fundamental principles of computation. Thank you for joining me on this journey. I hope you have a great day. And if you have any questions, you can ask me now. Thank you and have a nice day.